Okay. So for the very first thing, which is basically define a gravitational field. So this question will be there all the time. And to do this, let's go start this off. So gravitational field is defined as the region. Let me just write it down. So you can write region. You can also write space, right? Region where a mass, writing mass is the keyword, okay, here, experiences, where a mass experiences a force of attraction. Okay. You can just get away with writing force as well, so that's fine. Now, so what I want to tell you is that if you see gravitational field from a distance far, far away, so let's put this Earth. So Earth has a center. So it would act as a point mass. So this is basically a point mass. And the reason we call this as a point mass because the gravitational field is always directed towards a single point within the mass itself, like this. Okay. And the field is radial. Like it's pointing towards that point, that single point in the center. And radial field means that it's basically like circular, right? So this is, I'm going to write radial field, which means the field itself is like this, the dotted lines, right? So this is the field, and the field lines are drawn like I have in red. This is the field around it. Okay, like this. So as you go away from the mass, obviously the field strength reduces. But if you see the field from very close, like right now, like if we see around, so Earth seems like it is flat, and the reason why it seems flat is because if you just look at a single small portion of Earth, obviously at a very small angle, right, like this. So obviously this part, which is this part, seems like it is a straight line. Every circle is like that, right? So we're looking at that small part. So what happens is that near the surface of Earth or any mass, the field seems to be like this. It's equally spaced and it is straight lines. So this is near surface of mass, right? And obviously here, this field that you see is a uniform field. And how do you know that it's uniform? Number one, it's equally spaced. And then it's basically straight lines like that. Okay. So for Earth, the gravitational field strength of Earth is 9.81 newtons per kg or meters per second square. That's the same thing. Okay, so you just have to remember that. Okay. Now, so then the next thing would be define field of force. Okay, so certain questions would be like that. And you don't need to, uh, worry about this because this definition it can come in electric fields, gravitational fields, or magnetic fields. So it's a common definition. I just wanted to bring it here. So field of force can be defined as the region of space where a particle, right? It could be a charge if it's a electric field or magnetic field, or mass, if it's a gravitational field, experiences a force. So basically, it's the same thing. You just need to change the say affected body, right? So it could be a charge or it could be a mass. So you just need to remember that. If you have any questions, do let me know. Now, written everybody? Should I go forward?
Yes, sir.
All right, so then you have Newton's law of gravitation. And for Newton's law of gravitation, just remember that. Wait a second, I forgot something. Oh my goodness. I forgot a huge thing. People are going to kill me now. Wait. Okay, anyway. So the Newton law of gravitation has the definition will be of 2 marks, right? The first part of the definition is when you got it right, number one, is that the force of attraction between two masses is directly proportional to the product of masses. All right, so this is the first mark. And the second mark is given when you say, and inversely proportional to the square of distance between them. And this distance is taken from center to center because we consider everything a point mass like this, okay? What essentially it means is that if you have two bodies, like for example, a mass like this and another mass probably like this. So let's suppose the mass of this body is m, the mass of small body is small m. And from here to here, the distance between them is r. So what Newton's law of gravitation is that force is directly proportional to the product of mass, and force is inversely proportional to the square of distances, the distance between them. So when you combine this, what you get is you get F equals to GMM over R square, because when you remove the proportionality, you also need to put a constant, and the constant, this constant G, is called universal gravitational constant. Now you don't need to remember this, obviously, it will be given, but still, to save time, you can do that. It's 6.67 times 10 raised to minus 11 Newton meter square kg minus 2. Okay, so you can always remember this. This is given in the exam, and you don't need to remember the units as well, so it's fine. Can you write this down, please? So the questions from this chapter will always be there. Like the second question or the first question is always from gravitational field. So this is a very, very important topic in terms of the volume of questions that they give, right? Okay, please hurry up, write this down.
Answer.
Okay, very good, very good. All right, now going forward then. So then, so now this law depends on certain assumptions as well, and we need to, remember those as well. So the assumptions are that number one, for all points, density of the body is constant. Like we just say that the whole Earth, let's suppose we talk about Earth. The Earth, whether it has water somewhere, whether it has molten, metals or whatever, rock, air, we say everything on Earth has a, a uniform density or just one value. So this is one assumption that we make. And the mass has to be a perfect sphere, any body, right? The third thing is that the mass will be in a circular orbit. That's how Newton's law of gravitation works. All right, so on these three assumptions, you can write this down. This is very important. Now, so the first question, it says a spherical planet of mass m and radius r, right? Okay, you can write this down first. It's okay.
Done, sir.
All right. So speaking of this part, it says a spherical planet has a mass and radius r. The planet may be assumed to be isolated in space and have its mass concentrated at center, as you can see. Okay. Now it says that the object of mass m rests on the equator of the planet. The surface of planet exerts a normal reaction force on the mass. And obviously it is going to be reaction force like this, right? Like that. Okay. Let's say force of reaction right now because there's R radius as well. You don't want to get confused. First of all, it says state formulae in terms of mmr omega for the gravitational force between the planet and the object. Okay, so the force of gravitation, as we already know, is F equals to gmm over r squared. So you just need to write that because radius is given in capital R, right? Then it says the centripetal force required for circular motion of the object. So centripetal force we already know in terms of omega, it is m r because radius is this omega square. Any questions? Please let me know.
So in the first part, we can use G because they haven't mentioned it, right?
No, but it says state a formula in terms of this. So we have to use the constant in any way. Otherwise, the formula would not be true, right?
Okay, yeah.
The next question is very important because it says the normal reaction exerted. We want to find this FR. The interesting thing is that you guys should remember that the force of gravity is here, right? Let's call this FG, okay? And because it is moving in a circular orbit, it means that in order, the sum of these two forces must have a resultant force towards the center, that is the centripetal force. Agreed? So technically,
Yes, sir.
the equation should be that the centripetal force should be equal to the force of gravity minus Fr. What do you guys say? Right? we want to find this Fr, which means Fr, the reaction force, should be equal to force of gravity minus the centripetal force, which means now we're going to write that the reaction force should be equal to GMM over R square minus MR omega square. Understood?
So why are you adding, subtracting? Why not add?
Because in the equation, these two forces are, resultant force. This is the resultant force, right? How do you find resultant? If I say this is like this force minus this force, they're in opposite directions, no?
Yeah, okay.
So then when you take FR to the other side, you have to bring FC to this side. So it will be FG minus FC. You agree, Ahmed?
Yeah, got it.
Okay, good. So this is how these 1 mark questions are. If somebody else have a question, please let me know. Both Fatijas are here today. Where are Fatijas? Oh my God. I always... No, Fatija is not in this class. Oh, damn. Okay, fine. All right, let's go.
So I have
Explain.
a question.
Yes, Anusha.
So FG acts towards the left.
FG will act, obviously, it is a force of attraction, so it's always towards the center, right?
Okay,
Anusha, has
got it.
seen any person getting repelled by Earth? Have you seen somebody getting repelled by Earth? Every mass gets attracted. So it will always, the weight of the person is towards the center of the Earth because that's the gravitational force, right?
Yeah, that makes sense.
Okay.
Sir, but like when two forces are added in the same, like when they go towards the same direction, they're oftenly added, right?
Yes, exactly.
So in
But
this case also it should be added.
you're saying FC should be added with FG?
Yes, to form FR.
Okay. All right. Moksha, I'll just tell you this. The issue is that you should always remember that this FC is not an active force. This is a result of forces. Do you understand? This is the resultant. So if there is
Okay.
a body which has a 5,000 Newton force acting this way, and there is a body which is 2,000 Newton force this way, so resultant force in this would be 5,000 minus 2,000. So by adding this, we are getting FC. Do you understand?
Yes, sir.
So you should understand the real forces are the reaction and G. The remainder of these are going to give us FC. That's why this equation forms. This is not an active force. This is not something that comes from, some force like a push or pull. This is the remainder of all forces that are acting. Do you understand?
Yes, sir. Now it's much clearer.
Yes. So do not never think that centripetal force is basically an active force. It is a remainder of all forces. That's why you should always remember that. Anyway, now in the next question it says, explain why normal reaction on the mass will have different values at equator and at the poles. Now this is a very important question. So to explain this, I'll just tell you this. You see, so when you look at the Earth, right? Earth is like this, right? Suppose we're just looking at this. So these are the poles. This is the North Pole. This is the South Pole, and the equator is on this side. Everybody agrees to this? Okay, like that. So a person who's standing on this side, which is the equator, the radius of that person from the center is R. Do you guys agree?
Yeah.
So then we can say that the force between Earth and this person is equal to GMM upon R square, right? But interestingly, or centripetal force, even if we say there's a circular motion happening, so centripetal force is basically mr omega square because there's a r here. So let's talk into centripetal force. That's easier. Now, when the person goes to the equator, he stands, sorry, at the North Pole or the South Pole. Now he's exactly here, right, on the line. What is the radius of this person from the center? His line of action is right here. So his radius from the center is 0. Do you guys understand this? So when, you know, about half year later, this person is going to come here, but that person will stay here. He will never ever move from his place. So it means he will never ever cause, like the earth is not causing any rotation to him. Do you understand? So what I'm trying to tell you is that it is very important to understand that there has to be a radius or a distance away from the center of Earth. If this person is exactly on the center of Earth, then obviously there will be no rotational effect on him, right? So for this question, for 2 marks, if I were you, I would write that the centripetal force is given by F equals to mr omega square. Okay. So as the person stands on equator, his radius from center is 0. Hence, centripetal force on him would also be 0. That's what you should be writing, okay? Wait a second. Hello? What's up? TikTok? What's up? Yes, in class. Call you later. Okay, bye. All right. So any questions, please let me know.
So shouldn't it be
No,
as a
sir.
person stands on North Pole, the radius will be 0?
Okay. If the person, sorry, my bad.
No, I meant you wrote equator. It would be North Pole, right?
Oh, yeah. Sorry, my bad.
So if we look at the picture from a different angle, we wouldn't see the person directly above the equator, right?
What do you mean?
I mean, we're
Like
looking
saying
from one
you
side. It
Earth,
should
if you look at Earth like this,
no.
still, even if you look at Earth from like this angle or this angle or any
Yeah.
angle, Earth still rotates like this, Kartika.
Okay.
It doesn't really matter. This person will not go from north and south do not go like this. They never go like this, right? So it's always like this or this. So that person will have no rotation at all with respect to Earth. Okay.
Okay.
Yeah. Do you understand now?
Yes, sir, I do.
Okay. Then in the next question, very clever, right? This person is very clever.
Sir, wait,
Please.
could you just...
Yeah.
No,
Yes. Okay. So in the next question, it says the radius of the planet is this, and it completes 1 revolution in this. What is this? This seems like time period to me, right? And this seems like radius to me. And it says calculate the magnitude of centripetal acceleration at the equator. Okay. First of all, I should remember that because I have time period, so the acceleration is omega square r. Do you guys remember this equation from the previous chapter?
Yes, sir.
Good. Suppose you forget about it. Let's suppose if you forget about it. All right. Just remember that because centripetal force is mr omega square and it is a resultant force, so you can compare it with like this. F equals to ma. M is m, F is f, A is r omega square. So you can just quickly, remember this. And if you want in speed, or velocity, so mv square over r, you can compare this as ma. So m is m, F is f, and A is v square over r. So you can actually quickly do this like this. Anyway, right now we need this. Also, we should remember, because centripetal, the circular motion is so important, because the third formula we should remember is that, let me write it nicely, okay? This is not good. So F equals to mr omega square. So you can compare this with ma, and you should see that A is basically like this. And then for the other one, F equals to mv square over r. If you need this, then you can compare this with ma again. And you should remember that this section is equal to this section. Anyway, the other formula you should remember is omega being equal to 2 pi over t, since we have time period right now. Okay, and we need omega. So rather than, finding omega first and doing all that, so you can do it directly. You can say omega squared will be 2 pi over the time period, which is 8.6 times 10 raised to power 4 whole squared, multiplied by the radius, which is 6.4 times 10 raised to power 6, like that. And then obviously use the calculator. Okay, Gatika and Nusha, be ready. Okay, now, so we're gonna write 2 pi divided by 8.6 times 10 raised to power 4 whole squared, multiply by 6.4 times 10 raised to power 6. So I'm getting centripetal acceleration as 0.034 as my answer. Okay. All right. So now I just want to remind you about something important here. Now in AS and A2, the rules are the same, that your answer, whatever you give, answer should be in minimum significant figures of data provided, or one more than that. Like if I had to write the answer, I would write 0.34, or I would have at max written it as 0.342. Okay. A person who writes the answer as 0.3, his answer will be wrong. So you can write 0.342. A person who writes 0.3 or a person who writes 0.3416, both will be considered wrong. So you have to follow this rule to make sure that you do not get a mark deducted in your exam. Do you understand? Okay.
Yes, sir.
Then about the North Pole. So one of the poles, so you should remember acceleration is equal to omega square r. And now since r at the poles are 0, so obviously acceleration will be 0. That is the reason it is just 1 mark. Okay. Finally, it goes here. It says suggest two factors that in case of a real planet cause variation in acceleration of free fall at its surface. Now, why would it change? Now going back to the assumptions we have made, right? So you go to the assumptions. I've given you 3 assumptions, right? And they're actually asking you these, okay? So you just negate them. You could say, so the planet is not a perfect sphere. And the reason it is not a perfect sphere because the radius changes from place to place. Understood? Then the other point is that you could just write that it's not the density at all points is not constant. Just negate the assumptions that we have made for Newton's law of gravitation to work. All right? Is that clear, everyone?
Yes, sir.
Yes. And obviously, it will not have a circular orbit as well because it is also influenced by other planets and things around it. So you should remember that. You can say, all right, the angle at that spins changes, something like that. So there's so many things, but generally this would be right. So you should always focus on this. Okay. So if you have any questions, please let me know. Both Ahmeds, Falak, do you understand this? And okay.
Sir,
Who
the
is
second word in the second point is density.
Yeah. The density at all points not constant. So Munib and Nadia, and who is Fahar? Fahar, are you new? This is my first class with you. Okay, Fahar doesn't like to speak then. Okay, Anusha, do you understand everything? And Mokshit and who's that? Suman and Ahmed, the other and Ahmed, Tanjim.
Yes, sir.
Okay. Aman, did you take AS class today?
Yeah, so I was there.
Okay. Aman. Oh yeah, you were there. All right, Fahar. Fahar, do you understand everything? Okay. Fahad, please get your mic fixed because we would love to hear your voice as well. Anyway, now let's going to the next thing. Now this question, and this question comes sometimes as well. So we need to, work on this. So explain why, although the planets and the sun are not point masses, the law also applies to the planets orbiting the sun. Now this is an important question, right? Because in the previous question, we have said that Newton law is based on assumption, and the assumption is that they're point masses. But now it says in reality they're not. But why do you think that the Newton law still applies on them? Any guesses you guys have?
Because
So
the
is it
radius is
because their separation is larger than the radius?
Yes, because the thing is that in reality, what happens is that if this is the beautiful sun and this is the green earth, so their radius, like their separation, if I'm not wrong, I think the separation of sun is from earth is 1.5 times 10 raised to 11 meters. I think. Let me just Google it. Wait. Googling. Okay. So if you look at the separation, I'm sorry, distance of earth to sun. Okay. So the distance is about 1.5 million. That's right. Okay, that's 10 raised to power 11. So this is the separation between them. And then the radius of Earth is 6.4 times 10 raised to power 6, which is very, very small compared to that, right? So it means that basically the separation of Earth from the sun is about 10 raised to power 11, and the radius of Earth is 10 raised to power 6. So it means that 100,000 times the distance is greater between them. Do you understand? With respect to the radiuses. So what we're going to say is, we're going to say, to answer this question, I would write that the separation of planet and sun is much, this is the keyword that you should use, greater than the radius of sun, planets, etc. Is that clear, everyone?
Yes, sir.
All right. Okay. Then you can write this down now, please. Okay. Now, the next thing we're going to do is the gravitational potential. The gravitational
Sir,
potential, yes.
before we move on, could you just quickly explain B part 2 again? Because I don't get it.
B part 2.
Yeah,
This one?
either one of the poles, yeah.
One of the poles. Why it is that? Okay. Look, Munib. This is Earth, right? Suppose. And suppose this is how Earth is basically tilted in reality like this. So this is our equator, right? Right?
Okay.
A person is standing on the equator. So if I say the direction of spinning is like this, right? So what would be the radius of this person from the center? This would be R. What do you say? There's a distance, right? So if I use F
Yeah.
equals mr omega square, I can find the force on him. Do you agree?
Yes.
Now, if a person is standing here, what is the radius from the center with respect to
It's
this?
still
Huh?
R.
No, it's 0 because it is exactly on the center.
But aren't we taking the distance from the center point to the
No, you do
Earth's
not.
surface?
No. This is what I'm trying to tell you. You do not take the radius perpendicular to the direction of movement. You take the radius like this, parallel to this, like this. Do you understand? That's
So
what I'm
you
saying.
don't take it in the perpendicular distance, just the parallel one.
Yeah, because what you need to understand is that the acceleration, the weight of this person right now, the weight of this person is acting in such a way that he's standing our distance away in the movement, right? So even if you realize this person after a while will come here. Don't you think so?
Yeah.
But this person will only spin like this on the same point. He will never go anywhere else other than North Pole. Do you understand? So
Yeah.
Earth is spinning in this direction. Earth is not spinning in this direction. So you
Okay.
don't expect this person to move here, or do you expect this? Or do you expect North Pole to come here?
No.
That is the reason. Do you understand? So
No.
North
Okay.
would stay there. That's why everything will move. Understood?
All right.
So
Yes.
that is the reason we take that the radius from the center with respect to the North Pole is 0. Okay, like that.
All right.
Okay.
So thank you.
All right. Now, so then going to gravitational potential. Now, gravitational potential is the most recurring definition ever. And this is also a tricky one. So the first point, it will be of 2 marks, by the way. And the first mark will be just writing work done per unit mass. Writing work done per unit mass is the keyword in moving, right? So this is the first mark. And the second mark, from infinity to a point, that's it. You can also, write to a point within the field if you want to, but that's not required, okay? Now, why this is a tricky one? Because this is the M1 mark. M1 carries, it means method mark in the exam, and this one is A1 mark. If you write the second point and do not write unit here, if the first point is wrong and the second is even correct, so you get no mark at all, right? You only get credit of 2 marks if you write both the points correctly. Do you guys understand this?
Yes, sir.
So make sure you do. The symbol of this, obviously, is going to be phi, like this one. And it is given as work done per unit mass, right? Now, so you should remember that what we actually mean from this particular part is that there's a slight derivation that is, required in this. Okay, so we're gonna look at that in a bit as well. So first, let's look at the SI units. So the SI units for this would be joules per kilograms because it's work done per unit mass. And then it's a scalar quantity. The reason it is scalar because obviously it is this. Okay. Anyway, now, did I give you the definition of gravitational field strength? I haven't yet. Okay, I'll explain that in a bit. Okay, so now just look at this. So basically what it means is, suppose this is some sort of, planet that we're looking at. Oh my God, I hate this. Wait. Okay. So suppose this is a planet we're looking at, and the planet has a certain radius, all right, at this point. And this is different points in that field, like this and this and this. So what I'm saying is that suppose if this is point A, and this is point B, and C, and D, E, and F, doesn't matter. So very, very far away from this, you have like infinity distance away. So this is basically, if this is the radius R, this would be 2R, this will be 3R, this will be 4R, 5R, and R is equal to infinity away. What they're saying is it is equal to the work that you do to bring a unit mass to a certain point within the field, wherever you want to bring it. That's what it means, right? Now, from the infinity with respect to that. Now, here, just look at this, because we can say that work is force times the distance. In this, the distance would be R over M, like this, right? Okay, so now let's keep it here as the first equation. And we also know that force of gravitation is gmm over r squared. So what we can write is that we can say that then this would be equal to something like, g mm over r squared times r divided by m, right? Like that. So I have substituted this part right here. Okay. So if I do that, then basically what happens is that this becomes equal to r and square cancel out, m and m cancel out. So this becomes equal to gm over r like this. Okay, because one r and small m cancel out. Now, this is entirely because now this is just a general thing that you should remember. This is not exactly correct because the potential is always, just remember that at infinity, potential is maximum. And then when you come closer, the potential is always negative. For that factor, let's look at this. So if I want to, find the change with respect to this, so the potential at any point is going to be the potential at infinity minus the potential at some random point that we're looking at, right? So let's say any point maybe. Let's like not here. So now potential at infinity, because it is infinitely far. So our formula is Gm over r at infinity minus Gm over r at some point. So if you find the potential at any point, then infinity, if basically anything divided by infinity is 0, minus Gm over r. So basically the potential at any point will be taken as minus Gm over r. Now, so this is the small thing that you need to remember. What this negative sign, all right, this negative signifies that max potential is at infinity. All other points within field have negative potential. Do you guys understand this? So every other point will have negative potential. So what you need to understand is you can never be able to get to anything positive. So if a mass is moving, like if you're moving from infinity towards a point. So let me just draw this letter. I just clicked it. Wait a second. That. Okay. So what I'm saying is, if you are moving from any point towards, the planet or a mass, then we say that the uh, potential becomes more negative, right? If you're going from infinity towards the mass, and if you're going away like this, right? Then you say that the potential becomes less negative. It will never be positive. The potential can never be positive. Either it is going to get less and less negative or more and more negative. Understood?
Yes, sir.
So that is the point that I wanted to make so you guys can remember. Okay. All right. So for some reason, I made this mistake. All right. Now, one thing that I missed, and you might, you can write it now. So before we go into the graph of gravitational field strength, we first need to define, just add it into notes. I missed it while writing it. Gravitational field strength. So gravitational field strength is defined as the force of attraction per unit mass. The symbol of gravitational field strength is G, and G can be written as obviously the force over mass. Now, force is obviously mg, as you know. So now, because you guys need to remember, this is a small derivation that I want to show you. Force is given by gmm over r square. So we can write it as like G equals to gmm over r square divided by m. Hence, gravitational field strength is going to be gm over r square. You need to remember the SI units for gravitational field strength are Newton per kg or meters per second squared, because it's also known as acceleration due to gravity. And also it is a vector quantity. So it follows directions as well. Okay, you can write it down. If you have any questions, do let me know, please. Everybody understand this?
Yes, sir.
Okay. Yes, Nadia and Aman and Gatika.
Yes, sir,
And
understood.
Yes, sir.
good. Fine. I need water now. Now, considering this important part, I just need to tell you this. I'll tell you from the graphs itself. Okay. So first, we are going to draw the graph of gravitational field strength. Okay. So gravitational field strength graph is drawn like this. So you draw a something like that. Let me see if we have to draw. Oh, yeah. Gravitation. Okay, we can draw this later as well. Good. So G on this side is Newton per kg. And this is basically the distance R. So suppose we're looking at the gravitational field strength of a mass like this, which has a radius of R on this side. Okay. So this means that the gravitational field strength at the surface is going to be the maximum. And then outside, the gravitational field strength is going to decrease in a downward sharp curve like this. Okay. All right. Wait. Very sharp curve like this. Okay. The reason is that if you look at the definition, by the definition, you see that G and M, the capital G and M are constant, which means that gravitational field strength is inversely proportional to R square. So as you go twice the distance away from the center, basically it decreases by 4 times. And as you go 3 times, it would decrease by 9 times. So it keeps on decreasing like that, right? So this happens outside. But interestingly, within this, like from the center, you guys need to remember that at the center, the gravitational field strength is 0, and it basically is directly proportional. So inside, G is proportional to R inside it. All right, like that. So this is the graph for gravitational field strength. Okay. Now you can also prove this, that why it is like that, because you can say, number one, let me just change the color. Let me take this one. This blue looks nice. Okay. First of all, we assume that for any, mass, the density is constant. And density is given by rho equals to mass over volume. And what we can do is we can basically find the mass of anything by multiplying the density and the volume of the object, right? The second thing we know is that it's a perfect sphere. So to find the volume of sphere, we just need to do V equals to 4 by 3 pi R cube, like that. Okay. So then we can say that actually this mass right here can be written as m equals to density times the volume, which is 4 by 3 pi R cube, like that. Okay. The gravitational field strength is given by G equals to Gm over R square. So we can write it as G over R square and multiply mass value, which is rho times 4 by 3 pi R cube. So what I've done is here, I've just put this mass here, okay, just to remind you again. Now, if you see, You can then write it down as G equals to G stays there, rho stays there, 4 by 3 stays there, even pi stays there, R square, and there are 3 R's on top, 2 at the bottom, so the R just remains. So within this, you can see that actually within any mass, this value, these all values are constants. The only value that is changing is G and R. So we can say G is directly proportional to R inside. And that is the reason it is a straight line within the sphere. Is that clear?
So should we know this?
Not entirely, but it will be used. Some parts of it. So you should write it down. That's my advice to you. Okay. Okay. So does anyone have a class after this? Anyone?
Yes, I do.
What time, Anusha?
In like 2 minutes.
Oh no, Anusha. Because of Anusha, we have to end the class now.
Even I have
Okay.
a class.
Sorry?
मेरी भी class है. It was supposed to be like at 8.
Oh my God. Sorry, Falak. I'm really sorry.
I have
I was
chemistry after this.
with Sandaman.
G. Yes.
Okay. All right. Okay. So we will now stop this.